Well, I'm very, very honored to be here. And I have known the 4 predecessors who were Noyes chair before me. I think that's the totality. One of them still comes to the office next door to mine almost every day. The other 3, one has left. Ralph Boaz, who was, I believe, the first, is no longer alive. I thought a lot about what I might say in this lecture, and my first inclination was to try to give a lecture along the lines of this rather blurry guy here. See if I can make it a little clearer. But I consulted the dean's office and I said I'd like to give this kind of lecture, but I need a good blackboard. And it turns out that so I wanted to show this because it reflects a common conception of what mathematicians do. And that's really what I want to talk about a lot today, is what mathematicians do and why the common conceptions are wrong. So certainly one conception is this, that people fill blackboards with lots and lots of formulas and such. Another conception I learned from a friend of mine who was traveling to a professional meeting, and at the last leg he was taking a taxi, and he was chatting with the taxi driver about what he did, and the taxi driver said, so you guys just work with bigger numbers, right? that's also a misconception. So I thought it would be interesting to try to talk about as well as I can exactly what it is that we do. So I also thought about past advice that I've given people about giving lectures. So I haven't never given anyone advice about giving a lecture to a general audience. I did a quick calculation. I think I've given somewhere between 4,000 and 5,000 lectures on mathematics in my career, but never tried to talk to a general audience. Everyone, at least in principle, was prepared for what I was going to say. But I have given advice to PhD students who were going off to give the first big talk, a job talk. And one thing I said on occasion, said to them was, well, you should prove one theorem, and you can tell one joke, but you need to make sure that the audience can tell the difference. So I'm going to follow that advice myself today. I'm going to prove one theorem, and I'm going to tell at least one joke. So I want to start, though, by telling you what I often say to freshmen on the first day of class in the fall when they're new students. I commonly say, what can you tell me about the square root of 2? Now, the square root of 2 is a number which, when you multiply it by itself, you get the number 2. And there's a really fascinating tale from which we can learn some lessons, I think, about the history of this. But when I start talking with students, when I ask them, what can you tell me, they hem and haw. Sometimes they say, well, I don't, if you have a square that's 1 unit on a side, then the square root of 2 is the length of the diagonal. And they say if you write it out as a decimal, it goes on forever and it never repeats. Eventually, though, I can elicit from them the answer that I want, which is that it's irrational. Now, I was not expecting everyone here to be really up to date on these things, so I have a little crib sheet here for you. So what does it mean for a number to be rational? It means it's a fraction, p divided by q, and p and q are whole numbers. And if it's not a number like that, then we call it irrational. And that turns out to be a really fundamental and important distinction in terms of numbers and in terms of mathematical knowledge. So after someone in my class has managed to remember that it's irrational, I ask the following question: how do you know? How do you know that it's irrational? And that's the question that I really want the students to think about. And they will say, when I ask this question, some of the things that they said before. Well, if you write it out as a decimal, it goes on forever and it never repeats. And I say, okay, have you tried that yourself? And when pushed, they will say, well, it's because my high school teacher told me. And I say, well, I'm glad that your high school teachers are telling you the truth. But appeal to authority is not usually the way that we do research in a university, and it's not what we like to be the basis of students' knowledge. So I explained to them that we know this not because of the things you might think, which would include, for example, the scientific method. If you wanted to use the scientific method, you would make a hypothesis. There's our hypothesis. It's irrational. And then you would perform some experiments to test that hypothesis. Well, what kind of experiment could we perform here? We might take some fractions and square them and see if we got 2, but we'd get tired pretty quick and it wouldn't be all that convincing. We couldn't do more than a few hundred, or we could get a computer and it could do millions, but that still wouldn't be all that convincing. So the scientific method isn't really what works. Mathematicians are often thought to be people who use computers. That's another common conception of mathematicians. Well, you must be somebody who spends all your time just programming computers and running programs and looking at numbers coming out of computers. And so I ask, and our students now tend to know something about computers and computer programming. I say, can you think of something we could do with a computer that would help us answer this question? Can we figure out that the square root of 2 is irrational by doing something with the computer? And a little thought indicates that you can't. So what does work? And the answer is that we have a theorem. A theorem is a statement which has a proof. And a proof is a logical sequence of steps starting with something that you believe in or know about, and deriving something new to convince yourself that that's true. Now, this theorem that I'm going to talk about is the one that's up here, which says that if you take any whole numbers, p and q, then the fraction p over q, if you multiply it times itself, you get p squared divided by q squared. And p squared divided by 2 squared, no matter what you chose for your whole numbers, you will not get 2. And we know this because we have a proof, and I told you I was going to prove a theorem. This is going to be it. You're going to get it in a minute. But this is generally attributed to Hippasus of Metapontum, who was a Greek. He was one of a group called the Pythagoreans. Now, Pythagoreans were kind of an interesting group. I think today we would surely call them a cult. They knew Euclidean mathematics, but they were also mystics, They were vegetarians, strict vegetarians. And in fact, in reading about this, I learned that the word vegetarian didn't really come into existence until the middle of the 19th century. And prior to that time, vegetarians were called people who were partaking of the Pythagorean diet. So, Pythagoras was not someone who was particularly empirical either. I mentioned the scientific method. That wasn't something that Pythagoras was particularly interested in. He was interested in mathematics and arriving at new knowledge by pure thought. One example, though, I read about that I found rather interesting was he believed that women have fewer teeth than men. Now, this is a mistake that he could have rectified by looking in the mouth of his wife. But he, for some reason, didn't bother to do that. So, it's interesting when we have a theorem like this, what that means for, this really is our methodology. The theorem is the methodology of mathematics, and what does that mean for the kind of knowledge that we produce? All researchers are in the business of creating new knowledge. Mathematicians are in the business of creating certain kinds of knowledge, and by a methodology that's rather different than the other sciences. One consequence of that, of which we're proud, let me brag about mathematics a little bit here. One consequence of that, of which we're proud, is that when we establish some truth, it tends to stay true. But we commonly teach today ancient Greek mathematics. I've seen very little ancient Greek chemistry, physics, or biology that's taught in high schools or in the university. But we still teach Euclidean geometry, the geometry of Euclid. We still believe in this theorem for essentially the same reason. I don't know that this was the proof that the Paces came up with, but it was one presumably fairly similar. There's probably an apocryphal story that goes with this that I think also gives us some lessons. As the story goes, Hippasus, who was one of the Pythagoreans, and a group of Pythagoreans were taking a sea voyage, and they were on a boat. And Hippasus made this discovery, and he shared it with his friends, and it was such a shock to them that they threw him overboard, and he drowned. Now, we might ask, why did they throw him overboard? And there's a couple of answers to that. So one is he really upset their worldview. From their point of view, a number was a ratio. A number was of this form. One whole number divided by another whole number. Those were the only numbers that they knew about. So him proving that the square root of 2 is not rational was a tantamount to proving that the square root of 2 was not a number in their worldview, anyway. On the other hand, they had this square, 1 unit on a side, and they knew the diagonal had to be the square root of 2. Now, what could they have done other than thrown him overboard? It's interesting to speculate. You can imagine, had the discipline not been mathematics, where they were pretty much forced to accept the proof that he gave because they believed in, it's pretty hard not to believe a convincing proof. They were essentially forced to believe that. If they hadn't been forced to believe that, they might have reacted somewhat differently. They could have, for example, said, well, old Hippasus, he's just a crackpot, don't pay any attention to what he's saying, that's all nonsense. Or they could have said, listen, Hippasus, what you've got is just a theory, right? I think that the rational numbers were created by God and they're perfect, and all you have to contradict that is a theory. And I think we should teach the controversy. Or they might have said, heresy. Pacis is a heretic. We have to stamp out this heresy now. Let's throw it over. So the outcome of the last wouldn't have made much difference to the Pacis, but it certainly makes a difference to us that we still remember this. And not only remember, but that this is a part of our culture. So I want to give you that proof. So you'll have seen a proof and have a sense. Now this is only one slide, and it's the hardest part of my talk. It will be on the final. So what is the logical reasoning that lets us know that if you take a whole number p and a whole number q and you square them, you look at p squared divided by q squared, that you do not get 2. So if you take any number and you square it and you ask how many times can we divide it by 2 without having a remainder, that number of times is always even. So if you think, for example, of 6, you can divide it by 2 once, then you get 3, and then you can't divide it by 2 evenly anymore. But if you square 6, you got 6 times 6, you can divide the first 6 by 2 and the second 6 by 2, so you get 36, and that can be divided by 2 evenly 2 times. First time you get 18, and then you get 9. So no matter what number n you start with, if you square it, you'll always be able to divide by 2 an even number of times. Now if we take our numbers p squared and q squared that we're trying to prove something about, well, they're whole numbers, they're squared, so each one of them is divisible by 2 an even number of times. That means that if I take 2 times q squared, that's divisible by 2 an odd number of times, because it's divisible by 2 one more time than q squared is. And 1 more than an even number is an odd number. And once I know that 2q squared is divisible by 2 an odd number of times, and p squared is divisible by 2 an even number of times, I know something. There are these 2 numbers, and they're different. They have different properties. So it cannot be that p squared is equal to 2q squared. P squared is not equal to 2q squared, and that's exactly the same thing as if I divide by q squared as saying p squared divided by q squared is not 2. So if you didn't follow all that, I can hand you a piece of paper and you can take it home and study it. I'm sure if you'd like to. But that's an example of the sort of thing that we do. And here's the first answer to a question that is implicit in my title. What do mathematicians do? They prove theorems. It's a pretty inadequate answer, however. It really doesn't come to terms with the day-to-day life of a mathematician, or what's important to mathematicians, or how mathematicians value each other's work. So I want to expand it and get to put it in context and show you more about what mathematicians do. But before I can do that, I still owe you a joke. So I want to tell you a joke now. I hope I haven't raised expectations very high, because this is, after all, a mathematical joke. But it's one that I particularly like. So it seems there's a mathematician and a biologist and a physicist. And they are asked to observe some phenomenon and then, using the expertise of their field, to comment on it. So the event they're asked to observe takes place in a sealed room with one entrance, no other access in or out. And 2 people go into the room, and a few minutes later, 3 people come out. So the biologist says, well, it must have been reproduction. It was a pretty short time, but that's the only possibility. And the physicist says, well, a conservation law has been violated, so it must be an experimental error. That's the only possibility. And then they ask the mathematician says, well, I don't know what happened, but if another person goes in, the room will be empty again. Now, people who lasted here tended to be more mathematicians. And that's because they appreciate that this is not all that far-fetched. It's not all that far from what mathematicians do. We don't tend to talk about negative people, but we do talk about negative geometric objects. We teach our graduate students about triangles and line segments and tetrahedra, which we multiply by numbers, we add, the whole basic course in algebraic topology deals with adding triangles, if you will, adding triangles and line segments, canceling them out, and even multiplying them by numbers like a half. And it's important to understand when I say a half times a triangle, I don't mean like the left half of the triangle and the right half of the triangle. I mean 1/2 of the whole triangle, whatever that means. It even makes sense, and we commonly would talk about the square root of 2 times the triangle. And I found that a little bit intriguing thinking about this, and I thought for a while if I couldn't alter this joke so that the punchline came out about the square root of 2 times a person, but I couldn't really figure out a good way to do that. So I'll say a little more about the joke, but let me enhance my description of what mathematicians do. So there's 3 steps. The first step is to create an abstract model of a physical phenomenon or some other part of mathematics. The second step is to study the model, and to study the model as an end in itself, as an object intrinsically interesting. And that's where we create new knowledge, typically by proving theorems. And the final thing is technology transfer, you might call it. We take the new things that are learned from this model and transfer them back to the mathematics. And I wrote here, rarely to other disciplines. The rarely is there because the question was, what do mathematicians do? And it's actually rare that mathematicians, I think, do the technology transfer back to some area outside of mathematics. But it's very common for people in other disciplines to come to mathematicians and learn, we hope, that all the model that they wanted already exists and has already been studied, and quite a bit is known about it, and then those people often do technology transfer back to the other disciplines. Now, let's illustrate these things, for example, with my mathematician from the joke. Right? He had an abstract model of the phenomenon that he was interested in studying. His abstract model was the integers. And he knew about arithmetic. He didn't have to prove any theorems, they were already done. And he knew that if you start with 2 and so his integers included the negative integers, of course. If you start with 2, you take away 3, then you need to add 1 to get back to 0. And where he screwed up and made himself an object of ridicule was in the technology transfer segment. He applied it in a place that was inappropriate. It's also good to think about these 3 things in the setting of hypasis. So hypasis, the Pythagoreans and the Greeks had this great geometry. Now geometry was already an abstract model. They had ideal lines that extend infinitely far, ideal triangle points which have no extent, which means they have no dimension, just no dimension. So they had this rather abstract model of Euclidean geometry, and they then went and made a further construct of numbers and the rational numbers, because they wanted to do things with the lengths and areas that occurred in geometry. So they needed to add lengths, so they needed to add rational numbers, they needed to multiply because they wanted to calculate areas, they needed to divide because an extremely important concept in Euclidean geometry is the notion of ratio. Two lengths, these two lengths have the same ratio as these two lengths. And what Hippasus did was to prove, using mathematics, that their model was inadequate. So they had a model of which was the rational numbers, which was supposed to be modeling geometry, and there was this length, the square root of 2, the diagonal of a square, which wasn't in their model. And that's why they were fairly upset with him. Technology transfer, I also like to mention to young mathematicians, is something that should be attempted warily. This step, at least when you're transferring outside mathematics, is not mathematics. It's using mathematics, but it's not something that is amenable to proof. It's not something that is amenable to the technique. So the best example of all, in my view, of an abstract model of some part of mathematics is one that's due to René Descartes. So Descartes gave us what we now call Cartesian coordinates and analytic geometry. But what he did was look at geometry and create an algebraic construct which modeled the geometry. And one could prove theorems about equations, elements of algebra, and translate those back to learn deep things about the geometry, the Euclidean geometry. We are still today doing a lot of stuff that Descartes did. There's a good segment of my department who's engaged in understanding algebraic models with the hopes of gleaning geometric information from those models. So I promised in my title that I would also talk a little bit about dynamics and some examples there, and some examples of this abstraction that I think is the heart of mathematics. I hope by now that I convinced you, this is almost word for word what Brian has said, but I hope by now I've convinced you that it isn't quite right. It should be dynamics is the study of abstract models of how things evolve in time. Now, I want to see what my next slide is. Oh yes, I knew I was going to forget this. So I talked with my wife about some of the things I was going to say in describing dynamics, and I said, well, I'm going to do this and this and this and this, and she said, well, at about this point, your audience is going to be saying, oops. Your audience is going to be saying, why should I care? So I thought it would be good to preempt that question right now, before I start talking about it, and address this issue. There are many answers to this question, and you've all heard some of them. So from there's the argument by utility. Now, I don't want to dwell on that very long, but from the point of view of a professor, when a student says, why do we need to know all this stuff? One is very tempted to say, listen, kid, without mathematics, your iPod wouldn't work. Think about that. Another argument that one hears less is cultural. So the mathematical knowledge that we have is a key part of the culture of Western civilization and other civilizations too. But particular, I would say that the mathematics of Euclid is every bit as important for our culture as the works of Homer. I would say that the mathematics of Newton is as important in our culture as the works of Shakespeare. So those are two important reasons, but they're not the reasons that a typical mathematician has when he decides to sit down or decides what he wants to do. The reasons that a mathematician has have to do with the fact that, at least in practice, we tend to be Platonists. We tend to believe that 2 and the square root of 2 actually exist, have an existence in our universe, and we are investigating their properties. We discover new results in mathematics, in my view. We do not invent them. Had Hippasus had his choice and been making an invention, he would have made the square root of 2 rational. I have no doubt. He didn't have that option. I think that its intellectual curiosity is certainly the primary motivating factor for most mathematicians that I have known. And I think that knowledge about mathematics is every bit as real and equally important to knowledge that we gain about subatomic particles or the cosmos. So, having said that, let me tell you a little bit about dynamics. And then I want to put up a couple of pictures here. I had a discussion earlier today with Bryna and remarked on the fact that I was only showing pictures of dead white men, but be that as it may, they're not ones that you're necessarily familiar with. So Henri Poincaré was a French mathematician of the latter part of the 19th century and the early part of the 20th century. And I'm going to talk about some work that he initiated and was completed by George David Birkhoff, who was the first really famous American mathematician. The first American mathematician who made a name for himself in Europe, which was then the intellectual center of, at least in mathematics, and probably in most things. My colleague, Paul Gors, has said to me more than once, you're really lucky in that your area, you can, there are concrete things you can talk about and tell people what you do. And there's some truth in that, but let me emphasize what I'm doing is there is an abstract model about which people have proved theorems, and I'm actually going to try to tell you something about that. But then there are concrete instances of that in physical or idealized physical phenomena, and that are much easier to explain and are not available to people like him, I think. So what I'm going to talk about is a billiard game. But we're not going to use a rectangular table because that's it's too easy. But we're going to make it, so we're making it harder by using a table of this funny shape. On the other hand, we're going to make it easier. We're only going to have one ball. And the object of the game, if you have, there are no pockets here either. This is billiards, right? Not pool. There's no pockets here. So when you only have one ball, what could the object be? Well, the object that I want to talk about now, there are many objects, many interesting questions related to this, but the one that I want to talk about is, can you find some place to put your ball in some direction to shoot it so that it comes back exactly where it started, going in exactly the same direction? So, of course, this is a frictionless table. So once you hit this ball, it's going to go with, and there's no spin in this game either, right? There's no fan. You can't put spin on the ball. You get to shoot it straight, and you bounce off the sides according to the usual rules, the way billiards work. And you want to know, is there a way to do it so that you come back exactly where you started? And this is an instance of a problem that, as theorem of Poincaré conjectured and proved some special cases of. It used to be called Poincaré's last geometric theorem, but it was finally really proved by Birkhoff, who thereby made his name, because this one thing made him well known in Europe. So there's a little more to this than just getting one thing that comes back. There's a notion of speed, but it's an abstract speed. Everything here is abstract. This is not like feet per second. It's revolutions per bounce, I guess would be the units here. So if I had, and my pictures are physically certainly wrong, because it's hard to find these things, and if you just try drawing one, I couldn't get them to work out quite right. But if you imagine a ball and it starts here and you shoot it off this way, it bounces off, hits point 2 on the rail, then it goes to point 3 on the rail, then point 4, and 5, and back where it started. So it's made one circuit, one revolution, and it's taken 5 bounces, so its average speed is 1/5 revolution per bounce. Now, you might say, well, I can imagine 1/6 or 1/7, but what about complicated fractions? And here's an example of at least sort of the shape it would look for 2/5. So here you start at 1, you go to 2, then to 3, then to 4, then to 5, and then back to 1. You've in some sense gone twice around, 2 revolutions around something, and it's taking you 5 bounces, so it's 2 revolutions per bounce is the speed of that. Now, here is then the billiard version of the theorem of Weinberg and Birkhoff. They said there always exists a solution to this billiard problem with any speed you want, as long as it's a rational number, one fraction divided by another, or one whole number divided by another, and that the fraction is between 0 and 1, then there's always at least 2 with that speed. There are some conditions. The table has to be what's called convex. That just means it's not horseshoe shaped. That you can from any place you put your ball, you can shoot it and hit any place on the rail. You're not blocked by some other part of the rail. And smooth just means there's no corners. This is not like a real billiard table where you have corners. And to show that, let me point out a question that's unknown. You could become famous if you answer this question. Well, famous in some circles. So if you take, every triangle has some way to shoot this ball so that it's periodic. There's a lot known, and this is a well-studied problem. It is known that if every angle in the triangle is a rational number of degrees, then there are lots of such things. But for every triangle, some with irrational angles, and for reasons I can't explain, that includes most triangles. We don't know. So now I'm going to try to go a little farther and really state a serious theorem. And so there it is. I'll come back to it. Let me show you the picture, and then we'll come back to it. So this is a theorem. This is the real Poincaré-Birkhoff theorem. It's a theorem about a cylinder. So you have a cylinder, which is the outside of a tin can. There's no top, there's no bottom, there's nothing inside. It's just this finite cylinder outside. And you have some transformation of this cylinder. The top gets rotated by 1 full revolution exactly. And the bottom is nailed down. You hold tight to it so you don't it doesn't move at all. And we have this fact about area, which turns out to be crucial. If you look at a little area and you look at the little transformed area, they're exactly the same. In that case, what Poincaré and Birkhoff said was for every rational number, for example, 1/5, there's some point which goes around this cylinder once in 5 hits from this transformation. There would also be 1 through 2 hits, so that would be something that after 5 hits, it came back to itself and it went around twice. All right, so I'll go back and we can just see what that says. It says, any area-preserving transformation of the cylinder which holds the bottom fixed and rotates the top 1 complete revolution has periodic trajectories with average speed, p over q, revolutions per iteration. And the picture is probably better than the statement. Now, why is that the same theorem as the theorem about billiards? And here I'm maybe a little ambitious, so don't worry if this doesn't immediately sink in. But I wanted to try to explain it anyway. So here is the billiard table, which now looks like an egg. And I think of my trajectories as starting on the rail, and they make a certain angle. And so they shoot off, and then they hit someplace else on the rail, and they bounce off with a new angle. And so that gives you a way of taking the hit points from your trajectory and making them correspond to something on the cylinder. The distance around the cylinder is the distance around the edge of the table. And the angle is the height. So you just have a plot of angle in degrees and position. So if I go from here, this point, and I hit over here, I have a new angle. That means I'm at a new point over here and at a different angle. That's a transformation. That transformation preserves area. But an abstract area. So it's not an area that's length times width. It's an area you can see here. It's length times an angle. So already we've got some sort of funny abstract area. We're going to see more. Now, I should comment a little about my own contributions to this study, which are an improvement of this theorem, which says if you have a cylinder and you have 2 points and they have average speeds S0 and S1, then for every rational number between those numbers, there's a periodic trajectory with average speed p divided by q. So what's important here is not that we have more general numbers than 0 and 1. What's important here is that the points whose speed we know don't have to be on the edge. In the previous case, the bottom was fixed, so that had speed 0. The top made 1 full revolution, so that had speed 1. Now we can do it with speeds somewhere in the interior, and that makes it a lot more applicable. So for example, we can come back to this triangle. Now I said we don't know about any triangle whether or not there are always periodic trajectories. But if you start with a triangle and you round off a corner the tiniest amount you want, now, the previous thing, the Poincare-Birkhoff theorem I couldn't use because of these flat sides. But what the improved version does is allow you to deal with flat sides. So if you round off the corners, there now are periodic trajectories, and 1 for every rational number between 0 and 1, because this is just another convex body. It's the same as the billiard problem for Poincare and Birkhoff, but they didn't allow flat sides, and for reasons that I'm not trying to explain, the improved version allows you to have flat sides. So that's one example of how it gives you new information. And then here's a completely different sort of billiards, and one that's much harder. So a little harder to imagine too. So I'm going to imagine playing billiards on a sphere. You have, there's no gravity here, there's no friction. You have a ball and you shoot it in some direction and it goes as straight as it can. In fact, what it goes along is what's called a geodesic. So the problem of finding periodic trajectories, if you're playing on a round sphere, this is kind of a dumb game, it turns out, because whatever direction you shoot it in, it goes around a great circle and it comes back exactly where it started out, going in exactly the same direction. However, if you distort this sphere a little bit or radically, making it bend in totally crazy ways, it was a problem of some standing for quite a long time to find out something about these closed trajectories of a billiard, which are actually have a name, they're called geodesics, and they're important in geometry. So Birkhoff knew that there was one. And subsequently people knew that there were three, I think. And it turns out that, once again, the solution to this, at least in part, comes back to a study of cylinders. And the cylinder here is rather like the one before. We have a point which goes to the next point it hits. You go sailing off and you cross in the back, which you're going the wrong way, so you don't count that. You wait till you come back and you're going the right way. And then you started with one angle and you get a new angle. So you get a new point and a new angle, and that gives you, again, a map of a cylinder, and it's still area preserving. Unfortunately, you don't know anything about the speeds. And that's why this is a much harder problem, and it's a good example of how abstraction can help you out, because several deep things that were there before I thought about this problem come into play. One is the algebraic topology, which gives you an algebraic model for some of the things going on. And another one is the statistical study of how things evolve in time, which is a field called ergodic theory. And that plays a crucial role in this also. So those abstract models, which were intended for something totally different, turned out to be exactly what was needed here. Oops. Oh. All right, so what's this? You might well ask, or not, what, beyond finding all these periodic things, what else can you say? What does this picture look like? And I should have told you that Poincaré wasn't really interested in billiards. He was really interested in celestial mechanics. So he was interested in the motion of the planets, or more honestly, an idealized model, a very simplified model. He only had three things in his model: two big point masses, like the Earth and the Moon, and a little mass like an Earth satellite that didn't really affect the Earth and the Moon, but was affected by them. And he made a pretty crucial mistake, thinking that something like this could not happen. That in fact there would be there would be nice curves that go through here, and that the points would tend to follow those curves. This is an example of what's called chaos. This is also a picture of what's called a Birkhoff region of instability. And there's an awful lot, when we know these things exist, Poincaré had this problem because he had no computers. Now we have computers, and I can just write down a formula for one of these things and run it on a computer and generate a picture, and it obviously doesn't all lie on nice, smooth curves. So this is actually a plot of just a few points, something like 4. Take one point and see where that point goes, and then take another point and another point. So each time you see where it goes, you make a black dot, and it is so complicated that you get this picture. On the other hand, all those periodic things that we talked about are still there. Because I only did 4 things, I only get one of them is this region down here, one of them is this sort of region up here, and there's probably 2 of them that give you this middle region. So you can understand why this is called chaos, and we understand a little about this. There's a lot more we would like to know. We would like to know, for example, what the area is. Is it possible that that black set has area, 0 area? It doesn't? We don't know that. It doesn't. What can you say about its area? I spent a long time studying this systems like this, and then I moved on because I said whatever I can say. So let me now say, well, we've talked about dynamical systems and about abstractions. It has this abstract notion of area, but in fact there are many, much more abstract notions of area that come in to mathematics. But just in the question of models of how things evolve in time, what's left that we might want to abstract? And the answer is, why not abstract time? Why should you think that time is represented by a single number? Or why should you restrict yourself to thinking of time as represented by a single number? So why not let time have dimensions? So you can have 3 minutes east and 4 minutes north, or 2 minutes south and 5 minutes west. Even more general is, instead of representing time by a number or a pair of numbers, why not represent it by a matrix, which is an array of numbers? And the evolution of time then is determined by multiplying these matrices. This is what Bryna made reference to when she talked about group actions. But that's really studying transformations of some space, some geometric object, where time is represented by a matrix. And one of the things that makes that particularly hard is that the evolution of the system, after you wait for time t, and then you look at it, and then you wait for time s, if you had done that differently and first waited for time s and then waited for time t, you would get to a different place. And that makes this kind of dynamics quite a bit more difficult than the things that we were talking about before. Well, I want to finish with a important principle of relativity that was observed by one of my PhD students. He actually discovered this in the middle of his thesis defense. He said, "It's amazing how fast time goes when you're up here and how slow it goes when you're So, in deference to all of you people on slow time, let me just say thank you."
So, is the fact that Birkhoff was an American mathematician and a major early in 20th century American mathematician, did that have a direct effect on the development of dynamic study of dynamics in the United States, do you think? Are we here now?
I suspect it did. I don't really know his mathematical progeny, but certainly his work had an effect on everybody. But I think it was, one thing important about it was the first instance where Europeans said, well, maybe we better look at some of these Americans. Because they might be doing, here's at least one case they really did something interesting. Any other questions? Yeah.
You're one of Birkhoff's profs.
Aha, is that right? So what's the connection?
Your advisor was Smale
Yeah.
and Bob.
Yeah.
Then there was Carmichael and Harold Mead and Mott Smith. And they were students of Birkhoff.
Okay.
So, yes.
So
To answer Ezra's
Wow.
question, yes.
Well, according to the Mathematical Genealogy Project, George Birkhoff had 46 students and 5,967 descendants.
You still have time.
any other questions? Is there a question over here?
I have a serious question. I've noticed at age 64, the length of a year is a lot shorter than it was at age 5. Like the time between birthdays and the time between Christmases, when I was 5, it seemed like
Right,
age 61 year,
right.
and now it seems like there's 60.
So I think, and I'm the age slightly older than you, and I have the same experience. I think this is probably a psychological phenomenon, and one possible explanation is that a year now is a much smaller fraction of your lifetime than it was when you were 5. So when you were 5, a year was 1/5 of your life, and that was pretty big, and now not so big. But I would actually defer to some of the psychologists in the audience if you really want a more authoritative answer.
You're right.
Well, speaking of which, you've addressed a lot of conceptions that we might previously know about mathematicians that have now been cast into question. There's also a perception, maybe it's actually more well known among mathematicians, that it's a young man's game, a young person's game. What's your feeling about that?
Tough question. I've heard various theories about this. So supposedly, famous physicist, maybe it was Gelman, said that it wasn't your age, it was the length of time. If you were going to do anything good, you would have done it in the first 10 years, no matter when you started. So that would suggest you should keep changing fields and start doing something totally different. I think, on a personal note, I don't have the stamina that I once had. That's absolutely true. In terms of advice for mathematicians as you get older, find young collaborators.
Any other questions? If not, please stay and join us for a reception out in the lobby and congratulate John on his new medallion. And if I could ask the people who have the chairs that are, the fire marshal probably would be upset about, if we could all let them leave first, and then we can move their chairs, and then the rest of you